So our next speaker is Professor William Jason Weiss. He's a distinguished chair in engineering at Oregon State University. He was previously a faculty member at Purdue University for 16 years before joining the Oregon State University. His research interests are on the cement and concrete materials, specifically focusing on early age properties, cracking, transport, and concrete durability and shrinkage, and the surface life of sensing and prediction. So he is the editor-in-chief of ACI Journal of Materials. He authored and co-authored more than 425 publications. He's awarded a lot of awards from RILEM and ACI. And he is a fellow of the ACI and RILEM committees. Professor Jason will give us a talk today about linking thermodynamic modeling with SCM reactivity to design efficient concrete mixtures that reduce the carbon footprint. So please, go ahead.
Thank you very much, Ahmed, and thank you for a great meeting. It's a great set of speakers we've heard from already today. I'm going to turn off the video here just to help people with a little bit of bandwidth. But what I'd like to do is I'd like to talk a little bit about how we're going to link thermodynamic modeling to make sure that we're using our SCMs and we're designing concrete mixtures the most efficiently that we can. We're actually going to use a reactivity test to better utilize the SCMs. And here I'm going to be very clear. We're not only talking about existing SCMs, but we're talking about new SCMs, such as the type that Doug talked about earlier, the harvested SCMs, or glass that was talked about a little bit earlier, or some of these other clay materials that we're talking about earlier. And we'll see how all of these come together. The work that's been done here has largely been done by Keshav, who's our PhD student who's working on this project and doing a great job. And I'm working closely in collaboration with Professor Burkhan Isgor on this work. So what I'd like to do is really give us a little bit of background, and we've heard a lot about this, but we know from this picture that appeared on the cover of the New York Times that the world is aware that the cement and concrete industry are at the center of the climate change debate. But it's important for us to understand that one of the main reasons that we're here is not necessarily because the material itself has a higher carbon footprint or has a higher energy per pound of material than other materials. A lot of this is driven by the volume that we're using. So what we're trying to work on are solutions that can really be scaled up and scaled to volume very rapidly. In addition to this, we know that in addition to our initial carbon footprint, we know that the durability and the service life of the systems that we're working on is also incredibly important. An example of this is we had done an internally cured bridge about a decade ago. And what we noticed was this internally cured deck lasted 75 years from our service life predictions. And it was replacing a bridge that had been there for 25 years, as had the 3 bridges before that. And if we start to look at that and we start to bring that together, what we're able to now say is if we're replacing a bridge every 75 years instead of having 3 bridges over that time, there's a substantial reduction in the carbon footprint of that structure by also considering the complete service life of the bridge. So what we're really trying to do here is we're really trying to couple these two concepts together, and we're really trying to bring this together and say the time for change is now, and the time and how we're really adopting this or looking at these systems, we really need to look at that. We need to look at this as we go here. We really want to look at our sustainability, but there's really going to be 3 areas that we focus in on. The first is we have a lot of mixtures that we can reduce the cement content in. We can optimize these systems. We can take out a lot of binder in these systems, and we can make them much more sustainable just by optimizing the systems that we're looking at. And I think we know this when we start to look at mixtures that have way too much powder, way too much cement in the system. The second thing that we're going to talk a lot about is how we can look at the carbon footprint and really this cradle to gate phase by reducing the clinker factors in our concrete. There's a lot of alternative SCMs and a lot of innovative ways that we can go about looking at this. We've got some cellulose additives that we've got a big test site coming up with that allow us to reduce the clinker and get the same overall performance. But in addition, we can actually start to talk about the carbon footprint, where we're looking at cradle to grave phases when we start to bring in that permeability and we start to bring in the freeze-thaw and we start to bring in the overall performance criteria for the concrete systems that we're looking at. We start to bring in the service life. So what I want to do is really talk about how we're using modeling that's really trying to tie these three aspects together as we move this forward. I think, when we start to talk about modeling, a lot of times people get nervous and they say, well, why are we using a computer model, or why are we using these other things? And I want to just point out that there have been models that have been used in concrete for well over a century, right? We know mathematical models have existed. We even can go back to Ferret's model, where he was describing a model that said we could relate the strength of our concrete to volumes of things like air, water, and cement. We know this became the model of Abrams' water to cement ratio law, which is actually at the heart of a lot of what we do in our codes. Powers and Brownyard, we're going to actually talk about their work, but they were using model systems to describe performance. And this actually has amplified over the years. And we can see this in the NIST model. We can see this in the Mike model from Switzerland. We can see a lot of different models that have come along. What we're doing is we're essentially saying we're going to utilize some of the concepts in these models so that we can take some of the foundational principles and we can predict the reactions between cement and supplemental cementitious materials. What we're going to do here that's a little bit unique compared to what we've done historically in a lot of these other systems is we're going to consider the constituent material chemistry and the reaction products, the pore solution and the pore spaces in these calculations. So for each system that we're simulating, we're doing this for the specific materials that are being tested, for the specific cement that's being tested, for the specific SCM source that's being tested. And one of the real values that we have in this is we've been able to build up a database where we can place in all North American cements. We can place in all the fly ash sources that are being used. So we can now start to simulate a wide range of the materials that are being used. The work is largely divided into two parts, a part where we're going to talk about the equilibrium reactions. So this is sort of our classic thermodynamics and Gibbs energy minimization. And then we're also going to bring kinetics into the discussion so we can talk about the speed and the rate of the reactions. And this becomes a very important part of this. And really what's crucial in this, it extends a lot of the work that's being done in thermodynamics to both concrete, but also to service life modeling and some of the service life modeling concepts. So if we take a second and we think about this, what we really want to try to do when we're thermodynamically modeling these systems is we're going to start off with our water, we're going to start off with our cement and our cement chemistry, and we're going to bring those together and we're going to put those together with the volumes of the materials, and we're going to use some of these modeling predictions. Now, what the thermodynamic software is going to be doing in this, or Gibbs energy minimization, is it's going to say, if I start off with a known set of materials, my known cements that are shown here in kind of the reds and the grayish colors, and I start off with water, I can now start to figure out what reactions would form as these materials are enabled to react or come to a sense of equilibrium or a state of equilibrium. And you can think of this a little bit like having a puzzle, a box with all the puzzle pieces in it. So we're starting out with the puzzle pieces. And what we're doing is we're asking the question, what's the best way to fit all these pieces together? How do we get all the pieces together, all right, so that we can get to the lowest energy state? This allows us to determine the reaction products that are forming. And we're doing this based on the initial constituents that we have that are unique. So if you have a particular fly ash, a particular ponded ash, a particular specific type of material, we can bring that into the discussion and we can say, that's one of the initial puzzle pieces that we're dealing with. And over time, the cement, the SCMs are going to react with the water, and they're going to form these phases that we know, whether it's calcium silicate hydrate, shown here in gray, or whether it's calcium hydroxide, shown here in green. we can calculate how these are going to be produced over time. Now, the way that this is done is it's done in an algorithm inside of the program where essentially you're going to be able to take the initial constituents, you're going to be able to take the water, you're going to be able to put those together, and you're going to be able to look at all the different reactions that can form from the thermodynamic database. And you can pick the lowest energy state, which is essentially saying this is how all those puzzle pieces fit together best. And in doing that, we can then say these are going to be the reaction products that we get. Once we have those reaction products, we need to scale that up from the reaction products into what does this look like in terms of the structure of the overall material that we're looking at. So here, we're going to essentially say, we're going to now start to describe the porosity of the system, because once we take those reaction products and the porosity of the system, we can describe strength, we can describe transport, we can describe all these other properties. And this is really the heart of what Powers and Brownier did. And this is essentially the extension of what we're doing with the thermodynamic modeling. So what we're able to do here is we're able to apply a model called the Pore partitioning model. So we're going to essentially take the outputs of the thermodynamic model, where we have the initial cement phases or SCM phases that are going into the system. We have our initial water, and we're able to compute the reacted products. Now, once we do that, we can start to characterize these into the phases that would be more similar to what someone like Powers used to describe the overall system. So Powers described you have the cement phase and the water phase. They come together to produce the gel solids and the gel water. And if we overlay our products here, how we essentially go through and we identify these, we distribute them in the Pore partitioning model, we can essentially see that there's a relation between the Powers model, which is shown in the colors in the back, and the red lines, which is the thermodynamic model that we're showing here. So the real benefit here is we can actually link thermodynamics with a lot of the models that have been used over the history of time using this Pore partitioning concept. Now, when we do that, we can actually start to compare these results, and we can start to say, we can start to look at the predicted porosity of the paste in the system versus the experimentally measured porosity of the paste in the system. And if they fall along this dashed line, we simply have parity in this system, right? We have the fact that the model is predicting things well. And what you'll notice is for the systems that we're looking at here, we see a very strong correlation between the predicted porosity and the measured porosity in the system. So porosity is probably the easiest thing for us to be measuring and predicting. And this makes sense because this is really what the model is based on. Now, if we start to extend that, we can start to extend that to things like strength. And here we have a simple extension to compressive strength. And what we start to see is the variation starts to get a little bit wider, but we do have a fairly good correlation between the predicted compressive strength and the experimentally measured compressive strength, starting only with the initial chemistry of the system, the volume of the cements, the volume of the aggregates, and predicting this out. Now, if we also look at what these different symbols mean, you may say, well, what systems are we looking at? Here we're looking at OPC systems, but we're also looking at systems that contain ash. And what I want to point out when we talk about these systems is all of these ashes that we're looking at in this particular example, none of these ashes are in-spec fly ashes. These are all ashes that would either be harvested or be out of spec for one particular reason or the other. So one of the big values that this model starts to bring is it starts to allow us to identify alternative SCM sources or SCM sources that may not be the commonly used sources, where we could all of a sudden start to say, these make a lot of sense to be using for these concrete mixtures. These make a lot of sense for us to be evaluating. So this might be the type of an approach where we could all of a sudden start to look at a wide range of materials and say, yes, using these materials, these are the types of proportions that we would start off with in the laboratory on an experimental campaign to save a lot of time and to start looking at these are the optimal mixture proportions that the model tells us. Now let's start to do some trial batching before we start producing thousands of yards of these concretes. In addition, we've been able to use this to really start to describe for a lot of groups how we can start to make this transition from an ASTM C150 cement over to an ASTM C595 or Portland limestone cement in the system. And what we've been able to do is really start to build on a lot of the work that's been out there, where we're able to say, we could start to look at how the porosity of the system starts to change. And it's really changing because of some of the phases that are forming in the system. So all of a sudden, we're starting to replace some of the monosulfate with things like ettringite or monocarbonate or hemicarbonate. And we're starting to be able to describe the reductions in porosities that are occurring in those systems. And then that reduction in porosity translates over to a change in strength or a change in transport properties. So this has been very useful in explaining to people what's happening in these PLC systems. But in addition to this, one of the frequently asked questions that we've gotten when we're talking with state highway agencies and other groups about this is, if I use a Portland limestone cement, does that mean I need to stop using SCMs? And the simple and most direct answer to this is no, right? Keep using your SCMs if you're using a Portland limestone cement. So you're going to get a 10 to 12% reduction in carbon by simply shifting from an ASTM C150 cement over to a 595 cement. And right now we believe that there's 49 out of the 50 states that are permitting the use of a C595 cement. We're seeing a lot of transition over to this. And what we can say is, if your SCMs are silica based, you're essentially going to see the same type of performance. However, if your SCMs have alumina in them, what you're going to notice, especially as we start increasing the amount of reactive alumina in these systems, we see that there's a further decrease in the porosity of the system, a further stabilization of some of those phases. And we're going to see that essentially that reduction in porosity to get back to kind of a similar performance as what we started with, we're going to be able to go to a much higher limestone content in those systems. And this is along the lines of what Karen was talking about earlier with the LC3 cements. But this also starts to play into a lot of what we're talking about with using cellulose nanocrystals with slag and with some of these other materials, where we can now start to say we could actually utilize higher amounts of limestone in these systems, provided we have a reactive alumina. So all of a sudden, we're able to now start to design the amount of limestone we may want to have in these systems based on some of the other components that are there. So it's actually synergistic and beneficial to be using SCMs with these with Portland limestone cement, and it shouldn't be something that we're trying to take out of the mixture. So again, just to drive this point home, if you're using a C595 cement or you're using a limestone in the system, it's beneficial to use that with your SCMs, and that's really what we want to be doing as we move this forward. The other thing that I want to mention just really quickly, because this has come up and this has been something we've been looking at quite a bit with these modeling approaches. One of the questions that we were asked is, how does the Portland limestone system compare to the OPC system in terms of resistivity or RCPT or transport or a lot of these properties? And a lot of times people are comparing the OPC directly with the PLC. And again, if they fall along this one-to-one line, we have parity, and this is a good thing. And people really worry about this, do I see a slight difference in these systems? But the big thing I want us to do is sort of take a bigger picture out and look at this overall graph. These systems down here that I circled, the systems in black, these systems are the plain OPC or the plain PLC that we have in our system. There's no SCMs added. As we start to move to the right-hand side, what we notice in either the blue mixtures, which are fly ash, the red mixtures, which are fly ash with silica fume, the green mixtures, which are fly ash, which are slag, and the purple, which is a natural pozzolan, all of these show a substantial improvement in the resistivity of the system. So we see, first of all, that they move from a value that's down here to a value that's almost triple. In addition to this, what we start to see is that the limestone in these systems starts to see a little bit of an improvement off that line of parity. So we see the PLC itself is about 20 to 30% more beneficial in these systems, because partially of that reaction with the alumina phases. So how do we describe this in the system? Well, the first thing to note is The porosity of these systems is about the same, although it may be 2 or 3% higher. But the connectivity of the pores, which is a combination of the tortuosity and the constrictedness of the pores, decreases substantially in these systems. So we're actually seeing a huge benefit in terms of transport, a huge benefit in terms of service life, simply because we're using the SCMs and because we're using the SCMs with limestone in the system. So how do we start to integrate this and bring this all together? Well, the modeling approach and the approach that we're using here is we can actually take the chemistry of the OPC and we can bring that into the picture. And again, we have a pretty robust database where we've got all of the North American cements that we could find. They're placed in the database and we have that information. We can actually add limestone into the system if we want as well here. But now we can also add supplementary cementitious materials. This could be fly ash, this could be slag, this could be ground up shells, this could be all sorts of other materials. And as long as we know the chemical composition of the SCM, right, and how much of that material is going to react, this simulation can be performed. So what we're actually doing is we're performing a very rapid test where we can actually measure the heat release and the calcium hydroxide consumed and determine how much of this system is available to react. So again, this is modeled after some of the work that was done by Snellings and Scrivener. What we've done here is we've said, let's take potassium hydroxide, our SCM or our industrial byproduct, our calcium hydroxide, put those together and measure the heat released and the calcium hydroxide consumed. And if we do that, we can plot it on a graph that looks like this, where we can say the calcium hydroxide consumed is on our x-axis. So the more pozzolanic the material is, the further it is to the right. We can measure the heat that's released by the pozzolanic reaction. The higher it is, the more the reaction is occurring. And what we can actually do is for a pure silica system, we can plot out these reactions from 20% reactivity all the way up to 100% reactivity. We can do the exact same thing for alumina here. And essentially now, if we start to plot some of these SCMs that we're testing, we can start to tell you exactly how much of that system is reacting in these systems. So this may be a fly ash with 20% reactivity. This may be a silica fume that's almost 80% reactive in the system. And while we've shown here alumina and silica systems, we can also do the same thing for things like slags that fall into this category over here, where we can describe the role that calcium plays in that system exactly. So we can now come up with a numerical value for how reactive these different SCMs are. So all of a sudden we can start describing these in a way that is, we believe, much more telling than something like a strength activity index, because we're actually measuring the reactivity and it drives the entire modeling of the system that we're looking at. In addition to that, we're also going to have to bring in some of the kinetic factors. And in doing this, we've modified the classic Parrot and Kilo model that's been used for cements. And we've added several of these other systems in to get the reaction kinetics for a lot of the SCMs that we're looking at. We can now run this through the thermodynamic modeling, and we can predict the phases. So we can predict how much CSH, calcium hydroxide, is there, a lot of the other phases. We can predict the chemical shrinkage, the gel porosity, the capillary porosity. All of these things can be predicted. But in addition, we can also start predicting things like the pore solution, which is going to be important for things like ASR reactivity, the pH of the system. It's going to be important for interpreting electrical resistivity measurements. So we have the ability now to predict these things simply by knowing the initial chemistries of the overall systems that we're looking at. So we could take this entire model and we could predict things like the electrical resistivity or the formation factor. So here what we've done is we've shown the formation factor versus the air content of a mixture. And what we see is when the system is completely saturated, the formation factor or the electrical resistivity is dependent upon the air content, but we're able to use this model to predict the experimental results in these particular cases very, very well and capture these factors. If we don't vacuum saturate the system and we only saturate the pores, what we notice is these lines become flat lines that are independent of the air content in the system. Now that we have the formation factor, we're able to actually use the formation factor along with the ionic diffusivity of the different ions to start to predict the diffusion coefficients of the ionic species in our concrete. So now we're able to start to bring this in with reactive transport models and start scaling this up. When we start to do this, a lot of people say, well, what about the binding of the ions in the overall system? Well, what we're able to also do is use the thermodynamic model. And what's shown here in red are the thermodynamic predictions of modeling the binding of chloride ions in these systems compared to the black, which is the experimentally measured systems. And what we can see is there's a really strong correlation between simply taking the reacted microstructures and starting to calculate binding and doing the experimental measurements. So all of a sudden now we have the ability to take this approach and start to build it into a completely reactive transport model where we can capture the formation factor, the pore network, the porosity of the system, and the chloride binding, and predict things like the time to corrosion of a particular element simply by knowing the initial chemistry of the system. We can do the same types of predictions for things like freeze-thaw. All right, and I want to show one other example here where one of the major deteriorations that's happening in concrete pavements is this deterioration that's happening at these joints in these concrete pavement systems. This shortens the service life of a pavement. We get about 15 years before these joints have to be repaired, as opposed to 40 to 50 to 60 years that most people are seeing. And this is happening because of a chemical reaction. So the chemical reaction that's taking place is referred to as calcium oxychloride. It's the calcium hydroxide in the system, plus the deicing salt, plus the water. It forms an expansive agent. This expansive agent expands upon heating. And we can essentially have a really good prediction of this if we simply know how much calcium hydroxide there is in our particular mixture. Now, what we're able to do is we're able to design these mixtures to account for the fact that we can actually dilute the system by replacing a portion of the cement with something else. So maybe it's limestone. We can actually get to this dilution line. But if we also have something that reacts pozzolanically, we can take this further and we can now predict the amount of calcium hydroxide and the amount of calcium oxychloride that's going to exist inside of that mixture. So we can start to combine all of these items together and now start to go into a complete design procedure for a concrete. So let's assume we had a Midwestern pavement with no reinforcement. We wanted it to be resistant to calcium oxychloride and freeze-thaw damage. We can now all of a sudden come up with performance criteria or a response to the system where we're essentially starting to set our criteria for our mixture that say we want to have a certain strength, we want to have a certain workability. This is one that we're not predicting right now in the thermodynamic modeling. We want to have a certain transport property, right? We want a certain time to corrosion, and we know what that's going to be if we know our formation factor. We need to have a certain calcium hydroxide content to make it resistant to our deicing salt damage. We may want to specify a pH to help us out with our ASR in this system, and we can have a freeze-thaw time to reach critical saturation. We can input all of these as the performance that we're trying to meet with our mixture, and we can then start to come up with predictions simply using the software that can help us look for what the right mixture composition is going to be. So here again, this is an off-spec ash, right? And what we've done is we've plotted the water to binder ratio on the x-axis. We've plotted the SCM replacement level on the y-axis, and these contour plots are the compressive strength of the system. 20 megapascals, 25 megapascals, 30 megapascals, right, all the way up. Now, if we say that all of our mixtures have to have a strength that's greater than 29 megapascals, we can essentially draw our line here and say everything up above this line would fail to meet that criteria, right? We could do the exact same thing if we now start to look at our transport properties. So we can overlay contour lines for a formation factor of 100, 165, right, all the way up to a value of 500. And we can now say, here's our strength criteria. Here's our formation factor criteria. We can now start to add in some of these concepts like the time to critical saturation for freeze-thaw, which is met way up here. And if we bring in our calcium hydroxide, that actually says that everything below this green line wouldn't meet this criteria. So all of a sudden, what we've been able to do is with all of these different design criteria, we can consider them all at exactly the same time. And we can now start to define a feasible space with this particular SCM, this particular air content, that these are the mixtures that we could design that would meet this criteria. Now, would I run out and pave 10 miles simply by using this computer model? No. But would I use this to design where I want to be designing my mixtures for my trial batches? This is a much better way than sort of guessing or doing some of those other things if I'm starting off to try to evaluate and design these new mixtures. We can think a little bit about this like a fish finder. This isn't going to make the fish jump into the boat, but this is going to give you a much better idea of where the fish might be. So again, a little bit of where we're at with all this, and to summarize, we're really looking at using computational tools to enable us to get a better understanding of how to use alternative SCMs better, and to enable concrete mixture designs to really be elevated. We're no longer using a trial and error approach or an approach based on 1910 technology. We're considering all the design requirements right at the same time. We're using a Pozzolanic reactivity test. This can quantify the performance of SCMs. So this can give us a number that describes the SCMs, but it can also be used to drive the thermodynamic model. The mixture proportion approach can be used to optimize the reduction in carbon footprint of the system. The testing can be incredibly beneficial because it can be guided by this approach and really help us use our service life. And what we've done here is we've got the ability to completely link this with some of the concepts in the CEB model code, or link directly with the tests in AASHTO R101, which is the old PP84 performance specification. So we're now able to predict things that people can directly measure. So we're linking the simulation with the prediction with direct measurements, and we think there's huge value there. So with that, I want to thank you for your time, and I'm happy to answer any questions if we still have time, Ahmed.
Thank you so much. Actually, we have many questions here. So the first question is that you mentioned a comparison to Bauer model. Bauer's model uses inputs simply as a water cement ratio. So what are the models to this thermodynamic types of model?
So I'm not 100% sure I understand the question, but what we're using here is, so Powers use the water to cement ratio to predict things like the capillary and gel porosity. We're using the chemistry of the cement, the chemistry of the SCM, and the reactivity of these materials to directly predict the capillary and gel porosity. And then we're able to scale that up for several of these other predictions. Powers model is one that we'll use for strength, but we use other ones for transport properties or freeze-thaw. We use a lot of Fagerlund's work for freeze-thaw. We use a lot of reactive transport modeling for corrosion. So that's really where that direct link is made.
Good. The second question, what factors should be considered when using your prediction models? For example, the aggregate properties, curing, etc., are not considered as far as I saw.
Yeah, so these are actually considered. I didn't have time to go through those today, but we actually can go through and we can simulate the effects of improper curing. And we're doing quite a bit of work using neutron radiography to illustrate when these systems will stop reacting. There's actually a factor in the thermodynamic model that you can actually turn on that will describe how these materials stop reacting. And then you can start to predict things like gradients in the overall system. So that's a great way to start to build in the curing approach into the system. As we look at things like the aggregate properties, they're a direct input when we start predicting how the paste and the aggregates are going to work together, because now we're starting to use a composite model to start to scale that up. The one thing that we really haven't been able to do yet, or we haven't had the time to investigate, is separating the paste out from a paste component to an interfacial transition component, but that's definitely going to be something we work on as we start to move that forward.
Next question is that, can these models incorporate the effect of curing condition, that is availability of water to sustain the reactions?
Yeah, so as I mentioned, we do have a factor that's inside of here that actually addresses the curing, and we also use as a coupled portion of this, we're doing a lot of neutron radiography work to look at where those moisture conditions are and where we can describe those reactions and how that impacts reaction kinetics.
Okay. The following question said, what method or software was used in the model preparation?
Yeah, so there's a whole series of software. This is really built on a lot of the Gibbs energy minimization work, but then there's a lot of custom built software that goes into that. And if you wanted to send me an email, I'd be happy to send you papers that go along with that.
The following question, what approach is being used to go from a degree of hydration and thermodynamic models to a time for comparison with the validation data sets like compressive strengths, etc.?
Yeah, so we actually use the kinetic data. So we have a lot of kinetic information that we use that converts over from the rates of reaction into a time-based criteria. We use a lot of parent and kilos approach for the cements, but then we've added a lot of additional factors for the SCMs in the system. Okay.
So the last question: what it be possible to consider aggregate reaction and their expansion in the model?
So, conceptually, that's something that could be added. We've taken a very simple approach at the beginning to look at aspects of how the pH and the aggregates are related as our first simple approach. But that's definitely an area that we'd like to develop as we go further, because we think that there's a lot of, there's been a lot of people who've been looking at using microbial induced corrosion with energy minimization or ASR. There's a lot of work that's going on around the world, and these are all things that could be adapted here. I also noticed there's a question on air entrainment. And what I would just say here is, there could be a third axis that we draw here, which is the amount of air that's inside of the system. So as this air content gets smaller and smaller, this yellow triangle gets smaller and smaller. As the air content gets larger, this sort of forms almost a pyramid shape inside of those mixtures to account for the role that air plays. But this allows us to really start to compensate for the fact that we know that when we add air, compressive strength may decrease, but our freeze-thaw resistance is going to be beneficial, and we can start to play those trade-offs in what I would say is a meaningful and a numeric way, as opposed to just using rules of thumb.
Fantastic. Thank you so much, Dr. Jason, for this very good presentation. Thank you so much.
Thank you. Thank you for a great conference.
Thank you. So now